Hello, everyone, and welcome back to Kognito Key. If you've ever wondered how we manage to get incredibly smooth, stable power out of electrical circuits that, well, start off a little bumpy, you are in exactly the right place. Today, we're cracking the code on a brilliant piece of electrical engineering. We're talking about the choke filter, also widely known as the L-section filter. It's this fantastic tag team of components that totally revolutionized power supplies, and we're going to break the whole shebang down for you. Here's a super quick roadmap for today's explainer. First, the filter problem. Second, enter the L section. Third, how it works. Fourth, characteristics. And fifth, pros and cons. Let's get right to it. Okay, let's dive into part one, the filter problem, and those tricky early circuit issues. So, before the L-section filter came along, engineers were basically dealing with a massive headache, trying to smooth out the pulsating DC voltage coming from rectifiers. They essentially had two main tools, but man, both came with some pretty fatal flaws. On one hand, you had the series inductor. Sure, it smoothed the ripples out, but it severely choked the actual output current. I mean, it dropped the RMS and peak values significantly. It literally killed the current you actually needed. Then, on the other hand, they had the shunt capacitor. Now, this was super efficient at filtering, but it came with a huge risk. It caused a massive spike in diode current. That excess current could literally destroy the diode right there in the circuit. No way you want that, right? Plus, their effectiveness fluctuated wildly depending on the load resistance. They clearly needed something much, much better. And that brings us right to section 2. Enter the L section, the ultimate solution. The choke filter, or L-section filter, is wonderfully simple but incredibly effective. It's basically a perfect compromise. It takes the current smoothing property of the series inductor, right, and pairs it with the voltage stabilizing property of the shunt capacitor, putting them together into this powerful tag team. Here's the setup. An inductor is connected in series right after the rectifier, and a capacitor is placed in parallel with the load resistor. If you look at it physically on a circuit diagram, the way these two components sit actually forms the shape of an inverted letter L. Makes total sense. Moving on to section 3, how it works, specifically filtering those AC ripples. Now, what's really interesting here is the electrical journey that happens inside the simple L shape to clean up that messy, pulsating DC power. Think of this setup like a highly exclusive club. Step 1 is the inductor. The inductor acts as our heavy-duty bouncer at the front door. Because it has incredibly low DC resistance, but exceptionally high AC reactance, it happily lets the smooth DC walk right in, but firmly blocks the noisy, high AC ripples. But, well, no bouncer is perfect, right? Some tiny residual AC ripples always manage to sneak past. That is exactly where step 2, the capacitor, jumps in. The capacitor acts like a trapdoor. Capacitors uniquely allow AC to pass, but totally block DC. So any of those sneaky AC ripples that got past the bouncer hit the capacitor and are immediately bypassed straight down to ground. The result? Pure, clean, regulated DC power delivered perfectly to your load. Of course, as engineers, we can't just say, it works great, we need the data. Let's shift to section 4, characteristics and measuring performance. There are 3 absolutely crucial characteristics we care about here. First up is regulation. This measures how much the DC output voltage actually varies as the load current changes, and this filter handles that beautifully. Second, and arguably the most important, is the ripple factor. This is just the ratio of unwanted AC to the desired DC in the output. The lower this number is, the better. To minimize this ripple factor effectively, we really need high inductive reactance. In fact, filtering efficiency peaks when the inductive reactance, or XL, is approximately equal to 2 omega L, paired with a capacitor that has very low reactance to bypass the rest. Finally, we have critical inductance. This basically tells us there's a ceiling. You can only increase your inductance value up to a certain critical limit before it simply stops providing any additional benefit. So the crucial point is understanding exactly where this filter excels and where it falls flat. Let's wrap up with section 5, pros and cons evaluating the filter. The advantages are undeniably brilliant. By pairing these two components, the circuit provides vastly better voltage regulation than earlier designs, and you can easily vary the ripple factor based on your specific circuit's needs. It essentially solved the massive problems of its predecessors in one go. But there is a catch. The biggest disadvantage is its physical size. Inductors and high-capacity capacitors are incredibly heavy, and they're bulky. Because of this massive footprint, the choke filter has actually become entirely obsolete for modern, low-voltage power supplies. Today, things like your smartphone charger or your laptop power brick, they rely on tiny, lightweight IC regulators and active filters instead. But for the high-power, heavy-duty applications of the past, this filter was absolute magic. And that brilliantly illustrates the legacy of the choke filter. Thank you so much for exploring this fascinating piece of electronics history with me today. If you found this explainer helpful and you want to keep unlocking the secrets of engineering and technology, please make sure to hit that subscribe button to Kognito Key. Don't forget to like this explainer and share it with anyone who might need a little extra help with their circuits. Before we go, consider this. If a design this simple powered the early days of radio and television, what brilliant, simple combinations are waiting to be discovered to power the technology of tomorrow? Stay curious, keep learning, and I'll see you all on the next explainer.